Hello students, in this video we'll see two examples of using Hadamard's factorization theorem to prove results about the range of an entire function. Here's our first proposition. Suppose that f is entire and has finite order. Then f attains or achieves, or it takes on all the values, every complex number with one possible exception. Like the exponential of z can't be 0, right? That's an exception. Okay, so let's prove this by contradiction. So here's the proof of this fact. Proof. Suppose that alpha and beta are in C. Alpha not equal to beta, so they're two distinct values, two distinct complex numbers. And f of z is never equal to alpha, and f of z is never equal to beta. Okay, so in other words, this function f is entire in finite order and misses both alpha and beta are distinct numbers. Okay, so then what happens? Then what we can do is I can form f of z minus alpha. Now f of z minus alpha is not equal to 0, therefore f of z minus alpha is the exponential of g of z, right? For some g of z. Great. Now I claim exponential of g of z is not equal to beta minus alpha, right? Well, why not? Because what is this? Indeed, what does this look like? Well, exponential, of course. Exponential of g of z is f minus alpha. So this says that f minus alpha, if it was equal, would be equal to beta minus alpha, which would say that f is equal to beta, right? F of z is equal to beta, and that's a contradiction, right? So in other words, this thing over here cannot be equal to beta minus alpha. Great. What else do we know about g? Since f is finite order, since f has finite order, g of z is a polynomial by Weierstrass factorization, by Hadamard factorization rather. Great. Okay. Well, that's interesting because what that says is since beta minus alpha is not 0, I can take its log, right? That says that g of z is not equal to the log of beta minus alpha, right? That's impossible. That violates the fundamental theorem of algebra. This contradicts the fundamental theorem of algebra. Why so? You might say, well, wait a minute, like x squared is a polynomial, it doesn't get any negative numbers, right? Oh, but when you look at z squared, I can plug in I and get negative numbers, right? So we know if I say a polynomial is equal to a number, always has a solution, because you write that number on the other side of the equation, and you have the question of a root of a shifted polynomial. Therefore, we know that polynomials always have roots by the fundamental theorem of algebra. Therefore, these things are entire functions that attain every value. This is a contradiction. So I found two values that's impossible, which means that there has to be only one value this function omits. Beautiful, okay? We'll learn more about this. We'll see exactly, of course, how many times is it going to omit that value? Well, depends on what the order is, right? If it's n, you will achieve that n times, basically, right? Good. That's like an issue of valency. Here's the second proposition we're going to prove. Suppose that f is entire and has fractional, has non-integer, order. Then f has infinitely many roots. Okay, how would you prove something like this? Well, the proof goes as follows. Proof. If you try to write f of z as what? F of z would be e to the g of z, and then all of its finite roots, right? Let's say a1 z minus an, where here a1 through an, here a1 through an are the roots of f. And I'm assuming there's only finitely many of them. Okay? Well, what would this say then? This implies by what? We know by Hadamard that G is a what? It's finite order, right? So G has to be a polynomial, right? That G is a polynomial. And the degree of f and the order of f in this case is equal to the order of G. Because these terms, z1, z, that's a polynomial over here, right? Polynomials basically cannot give you anything else in terms of your degree, right? Because they're bounded by the exponential. They're just bounded by the exponential, right? So they can't increase the degree at all, right? Or can't increase the order. But that's a contradiction. Why so? That's a contradiction because the order of f was assumed to be non-integer, but it's the same as the order of g. And the order of g is an integer because it's a polynomial by Hadamard, right? So that gives you another illustration of how this polynomial is really telling you a lot of information. And so in particular, it says that if you are non-integer order and entire, you have infinite many roots. And a direct consequence of that, if you have infinite many roots, you achieve every value in the complex plane infinite many times, right? Why so? I'll just subtract off any fixed constant I want, and that proves that f minus any constant, say alpha, the roots of that thing, there's an infinite number of roots of that thing because subtracting off a constant alpha is not going to change the order at all, right? So if you have an entire function whose order is fractional, non-integer, or irrational as well, right? It will automatically have an infinite number of roots and it will take every complex number an infinite number of times, which is a very, very powerful result and is very useful in certain problems in number theory. Thank you very much.